Hey everyone, we're back for part 2 of our review of the 60 multiple choice question paper on ProProfs. We did the first 20 questions, and then we're in between that video and this video. I was hoping just to restart it where I left off, but unfortunately that hasn't happened. So these questions come up randomly when you start a quiz. So what we'll have to do is if we hit any of the questions we know we did in part 1, we'll just skip them and get to the next one. So that should get us sorted and heading in the right direction anyway. So let's jump into our first question. So which of the following inspection points is most critical to arc conditions for spray transfer in mag welding? All right. So we've got electrode coating, inductance settings, gas flow rate in all electrical connections. Right, so mag welding in spray is normally high amperage, high voltage. Like I would go with over 220 amps, over 24 volts as a good sort of like, that'll get you somewhere. It needs at least 80% argon in it to make it work. If you don't use an argon mixed gas, you will not get spray. So what would be best here? Electrode coating type. Well, that's not a mag question. That's an MMA, so we'll get rid of that. Inductance is used in dip transfer to reduce spatter, so we'll get rid of that one. Gas flow rate, okay, important to check because it's going to stop porosity. Electrical connections and contacts to make sure you've got good earthing and things. Now, so we're down between that C and D answer, really. Which is the most critical? I would say gas flow rate, because that's the one that's going to stop us from having porosity. Electrical connections, would I say I inspect them as part of welding? Well, we make sure the equipment's in good working order. So I'm going to guess here and go gas flow rate. Great, okay. What we got next? Solidification cracking takes place in carbon steels in the weld metal immediately after welding. So as the weld pool tightens up and solidifies up as you progress along the weld, it splits straight away. It's the formation of sulfides which come out of the steel or the weld metal, so it's contamination. Come to the middle, create polymer grain growth and all this type of thing. We have a video on the channel. Please go and find it. Watch that one. So that would be immediately after welding. You know, in most steels, we try to keep that sulfur content down to like 5 decimal points of 0. Is it? Yeah, 4 or 5 anyway. Really small. The only steel that really has a high amount of sulfur in it is something called fast machining steels, and it's something that you can machine on a lathe or a mill really easily. It's got what we call good chipability, and it allows for nice surface finish on machine components, but you can't weld it because as soon as you arc up, you get solidification crack because of the sulfur. Many of meters, instrument and controls on welding machines are not functioning properly, and their calibration certificates are also out of date. What will you do? Okay, so the equipment isn't calibrated, right? And you don't even think they're working. So what do you do? Well, you carry on, of course, don't you? No, you don't. Definitely don't. What would you do? So stop welding until corrective measures are completed to rectify the situation. Permit welding to proceed with no further action. Begin welding and then report to their management when the time is available. Using MAP, separate measuring instrument, and permit welding. Well, I think this first and last one is maybe very, very similar, because you could say that using something like a PALMS unit is going to fix that problem? I would say, for me, the answer here is stop welding until a corrective action is taken. That might be to fix the dials or to use a multimeter. I'm going to click this and I'm going to say I wonder if they put this as the answer, but I'm going to say stop welding until we get a corrective answer. That might be to use additional separate calibrated multimeters. Yeah, great. It might not be though. They might just say, no, you're not allowed to do that. We've got to get it fixed. You might not have it. Right. The welders have increased the voltage on an SAW set, so submerged arc welding set. What would be the effect on the weld appearance? I think this is fairly close to some questions you get in CSWIP homeworks during the course. So the thing here is to remember two things. In the main, amperage affects depth of penetration and voltage affects weld width. Okay, so anything that increases the arc length is going to widen the weld because it's like this triangle coming out. So the higher the point of the triangle, the wider the base. So increasing the voltage will increase the weld width. Great, that's a good one. If you watch part one, I'm desperately trying to make sure I read these questions properly now. I don't want that embarrassment again. When would you measure the minimum preheat temperature? Okay, so we have two things that kind of go hand in hand here: preheat and interpass. And what we've got is the preheat is the minimum temperature before we can start welding, and interpass temperature is the maximum temperature that we can't weld above. So of course, when we're welding, we've got an arc at 6,000 degrees, we've got molten steel at like 1,500, 2,000 degrees, something like that. And our interpass in carbon steel very often is a maximum of 250 degrees. So why that would mean you're always stopped. But what it means is when you stop welding, you take your temperature, and if you're above 250 degrees in the steel, you wait, you let it cool down. Okay. But before you start anything, say the first weld of the day or the first section of that weld of the day, you take your preheat temperature. So normally we take it 75 millimeters away from the weld prep each side and on the back of the plate or pipe if we can get to it. But it's immediately before we start welding, because that is when we need to understand what the temperature is. So our answers here are immediately prior to commencing the first pass and subsequent passes. Yeah. So if you say do one pass and then you stop and you go for lunch and you come back, you should take it again. Minimum preheat temperature measurements is only required if the heat input lower. Is that on this WPS? No, if you've got a lower heat input, you shouldn't be welding. When welding is completed, well, that's way too late. On the completion of each pass. Now, that would, for me, would be interpass temperature because we're going between passes. So preheat is before, so immediately before. In submerged arc welding, before starting the weld, you observe that the WPS was made with agglomerated flux. I think we did this one in part one. I think I have to answer it to move on. Classification for both is the same. And I said, you don't allow it, I think, didn't I? Insist it's the same as WPS. So, yeah, if you want a detailed one on that, go and look at part one. During root weld, which of the following would be main cause of lack of penetration? Okay, the root gap is too large. Well, if the root gap is too large, it tends to fall through quite a lot. So that's it. The root face is too small. So again, the face is small. It would be pushing through too much. The current is too low, or the preheat was not used. So like I was saying in a previous question there, Two things to remember. Current is generally penetration and voltage is generally weld width. So if the current is too low, we're going to get a lack of pen, or we have a higher chance of getting a lack of pen. Right, the correct joint preparation is very important since it decides the volume of weld metal. To be used high volume of weld metal deposition can. Sorry, I'll just try and work out the wording of that. To be used high volume of weld metal. Increase residuals. I'm going to have to read the answers and work out what that question is. Increase residual stress, give a longer service life, give superior corrosion resistance, be useful since the joint will have better strength. Okay, let's backwards kind of work this question because I don't know what it means. To be use high volume of weld metal deposition can. So I think it's saying if we use a high volume of weld metal, what will happen? Right. Let's get rid of stuff. So whenever you don't understand or you don't know, just try and get rid of some things where you just kind of say, well, I really don't think it's that answer. Right. Can be useful since joint will have better strength. That just sounds wrong, isn't it? Because strength is going to come from the mechanical properties of the joint, not how much weld metal you put in a sensible type way of thinking about it. Right. Give superior corrosion resistance. Well, no. Corrosion resistance isn't affected by volume of weld metal, it's type of weld. Give a longer service life. That would be joint design, so like blended toes, to allow that smooth transition of stress from the parent metal into the weld metal. So I would ignore that. So, but the more material you have, the more shrinkage and distortion they're likely to get, which you'll clamp to stop that from happening. So you should get an increase of residual stress. So I'm going to go for that one. Yes, great. So like that, proof, not sure what the question's asking. Do the ones you think you know, the ones you know, the ones you think you know, and guess the rest. And that was the one we were guessing. Just by using a little bit of logic and trying to get rid of things. Question 9. Post-inspection cleaning or further treatment of a component is not required in which of the following NDT methods? Okay, so let's say we've done a weld and it's covered in spatter. Which NDT method will not care that that is there? Doesn't mean it won't be seen. It means you can still carry out the test. So let's say it's spatter and you need to get rid of that. Well, ultrasonics testing you won't be able to move the probe back and forward and complete your scan if it's full of spatter. So we're going to remove that. Dye penetrant, all the ink will just stick around the spatter. You'll not be able to do that. The same with mag particle. So I'm going to say radiography testing is a way of testing with limited surface preparation. However, if it's absolutely covered in something like spatter, you may see that throughout the graph and it not allow you to accurately assess what the potential indications are. Which of the following may cause distortion? Okay, so we've got all of the above, even though it's on the top. It's randomly spaced out in these things, isn't it? Heating, stress, and contraction. I'd say it's all of those things. So we'll go all of the above. Nice easy one. Okay, right. According to AWS 2.4, so that's the American standard for welding symbols. If you do the CSWIP course, you'd be introduced to both AWS 2.4 and the ISO 22553 or 2553. Both of those ISO numbers come up in exams because some of the exam questions are a little bit older. Same standard, really. Just one's the more up-to-date version. So according to AWS 2.4, where does the symbol go for welding on the arrow side? So welding on the arrow side in AWS 2.4 is always underneath the arrow. If we're welding on the other side, it goes on the top. So we want below the solid line. And of course, we say solid line because in AWS, they don't have a hashed dotted line like we do in ISO. Okay. Right. When welding medium carbon steel plate over 100mm in thickness with basic electrodes, yeah, I think we did this one, didn't we? And I remember, I think I disagreed with this answer, didn't I? So I went with they don't need heat treatment if they've been used within 8 hours. They've been opened within 8 hours. And I think their answer was none if they were sealed in a vacuum pack immediately prior to use. Now, I said I disagree with that. I still disagree with that. And there's a big part of me still wants to tick this one that I know is it's going to tell me it's wrong because that's the one I think it should be. But I won't. I don't want to hit that score. No, I'm going to say it's that one. It's going to tell me it's wrong. I know, but I disagree with it. I think there is a time period from opening the vacuum pack and then moving it on. That's where we should be. Right, a tensile test. Oh, we did this one as well. Again, we went through the maths in part 1. 12.5%. Yeah, that's cool. Let's do that one. Weld decay. Okay, so stainless steel is caused by the formation of a compound with carbon. In the other element in this compound is, right, so it's a chromium carbide which is formed because chromium at between 600 to 850 degrees becomes what we call as mobile. So when we heat stainless steel up to that temperature, the chrome leaves the grain structure in which it's given corrosion resistance to, forms with this loose carbon that sits on the grain boundaries and forms chromium carbide. So it's chromium. So chromium is there to support the resistance to environmental corrosion. Nickel is there for acidic corrosion, which is why stainless steel can be used in so many things, because it has the best of both worlds. Okay. Hydrogen cracking is considered a cold crack as it will not form until the weld metal cools beneath. So that's 300 degrees. Yeah, got to be cold. I think we did that one the other day. A slag line is found in an MMA welds, are usually associated with not cleaning is the answer here. So improper cleaning between welds, the open circuit voltage being too high, the open circuit current being too high. There's no such thing as open circuit voltage, and that's to start the arc at about 80-ish volts. Some are a little bit higher, but 80 is a kind of rough average number for that. A low open circuit voltage would not allow the arc to start, because the reason we have that 80 volts is to jump the arc over the gap and make it work, and the voltage being too low. Okay, so I want to say improper cleaning between runs. Right, what else we got? When reviewing the WPS during welding, the maximum interpass temperature stated is 250 degrees. What would be the minimum interpass temperature? When reviewing a WPS during welding, the maximum interpass stated is 250 degrees. So that's our top end. What would be the minimum interpass temperature? Well, your minimum interpass temperature is your preheat value. So have we got an answer for that? So the interpass temperature is never stated on the WPS, yet it should be. Any temperature above 25 degrees would be acceptable. I don't agree with that. The welder would decide this. Yeah, no. Everything comes from the WPS. and the preheat temperature there, the last one. So we can go with preheat temperature. So you'll have two things on your WPS, preheat and interpass. Your preheat could be 80 degrees, it could be 150 degrees, especially if it's quite a thick material or it has a high carbon equivalent value. That preheat will be a lot higher. In GMA welding, which motor transfer uses a high and low current cycles? Oh, we definitely talked about this one in the last video, and it was pulse transfer. I would say high, well, peak and background current. I wouldn't term it high and low current cycles. During post-weld heat treatment, what is the sequence for a post-weld heatment? Say that again. Post-weld heat treatment chart. So this is a chart that kind of it starts and then heads up and then hits a soak temperature and then starts coming down, and that's where so we get. It depends how much we want to go into it. You have like unrestricted heating, restricted heating, soak, restricted cooling, unrestricted cooling. So let's see, do we have an answer for that here? Restricted heating, soak time, unrestricted cooling. That would be a bad idea. You'd probably get the wrong grain structure if you had just unrestricted cooling, especially above the critical transformation temperature. Have a look at our TTT diagram video. Unrestricted heating rate, soak time, restricted cooling. Unrestricted heating can lead to distortion and things not being generally right, so dimensional instability, so we don't want that either. Restricted heating, unrestricted heating, soak time, unrestricted cooling, restricted cooling, so they're the wrong way round. And then hopefully this one says unrestricted heating, soak time, restricted cooling, unrestricted cooling. There you go. So the unrestricted heating and cooling parts are when we're below the temperature at which we're going to change grain structure. In carbon steel, that's generally the number we say is 723 degrees. So as soon as we get below that, plus a little bit as a safety margin, then we can just let it cool however it wants. It isn't going to change the mechanical properties. So I need to click that one. Why essential to clean the surrounding parent metal adjacent to the weld metal made by MMA, which is to be ultrasonic tested? So why do we clean the weld metal either side of the weld? It ties into the question we had before. So we put a weld in. If you've got any contamination, any spatter, any slag, you know, anything like that on the surface of the material next to the welds, that's going to interfere with our NDT. So they say ultrasonic testing in this case. For ultrasonic testing, the probe has to be in contact with the material, with your couplant, so you get sound transfer into the part. Anything that interferes with that or stops you moving your probe backwards and forwards is going to be a problem. So here they've got paint. The answers seem to be paint. Questions, but you shouldn't have paint there because you've just welded it, so it should be clean anyway. Sound waves will not travel through paint. That's not true. Remove any rust. Well, you've welded it, so you shouldn't be rusty. Spatter could impact contact with the probe on the parent material. Yeah, I'll go with that. Spatter will reflect back echo signal. Right, okay, so I'm going to go with spatter could impact the contact of the probe. If you break the probe contact, you won't get a reliable result. Yeah, great. I think we skipped 3 or 4, so we'll go on a little bit more. Which of the following NDT process will best detect lack of internal sidewall fusion with mag? So internal, so very quick NDT lesson. We have 2 types of NDT, surface crack detection and volumetric. Surface crack detection has our dye penetrant and our magnetic particle testing, and that volumetric has our radiography and ultrasonic. So getting into the volume, anything we can see the inside of. Visual has always sat outside of that. It's been like the poor cousin of NDT. And it's changing, but you know, there's still a lot of standards that will give you acceptance criteria, and it'll say it acceptance criteria for NDT apart from visual or something like that. So here we want to do internal, so it'll be volumetric, so it's radiography or ultrasonic. Next question is, what are they best at? So radiography is best for anything that has volume because it works on the picture we're taking, seeing different densities of material. So if it's got porosity in, porosity is quite big for the radiation passing through, so we'll see it on the imaging plate, the photograph, for lack of a better word, that we're taking with the radiation. That means that it needs to have this change in density. Now, if it's a crack or a lacquer sidewall fusion, that area, that volume is really small. Imagine like a cross-section of a crack. It's infinitely small. So you may not have enough density change to pick it up with a radiograph, depending on the angle at which you hit the crack with. If you go through its thickness, it's got no density change. If you hit it from point to point, like through the length of it, then you might see it. Where ultrasonic works on strong reflectors. So if it's a straight edge, like a lacquer sidewall fusion, the sound will bounce back off that. But if it's porosity and it's small and it's round, the sound can actually pass around it, or you don't get very much reflection coming back at you. So it's easier to miss porosity with ultrasonics, harder to miss lacquer sidewall fusion. Radiography, easier to miss lacquer sidewall fusion, harder to miss porosity. So if we're looking for all of these defects and something that's very critical, then of course we may ask to do radiography and ultrasonics testing, right? But this one's just saying lacquer sidewall fusion, so ultrasonics. This comes up in Weld test specifications. 15614, 9606 require you, if you're doing mag welding, especially in short circuit dip transfer, that you do ultrasonics testing because of the risk of lacquer sidewall fusion. So we've got that one there. Right. Thoriated tungsten electrodes have a major disadvantage, that they are radioactive in nature. I think we talked about that one in part 1. Remember, and I'll take my time to say it again, thoriated electrodes, really good current carrying capacity. They work really well. They'd be my electrode of choice for TIG welding. But when you grind them, you need to now be thinking about capturing that dust, not breathing it in, because it's radioactive. People are getting lung cancer and things, and it's been tied back to this output. Okay, so we've got to look after ourselves. When examining a completed macro test, the recorded hardness figures were 5 HV points over the maximum permitted. What would your course of action be? So I'll give you an acceptance criteria. So 15614-1, non-heat treated material. The maximum hardness value is 380 HV. Okay. This is saying you've taken a test and it's reading 385. There's only one answer to that, and that's it's rejected. It's above the acceptance criteria. Now, that doesn't mean we're going to chuck the whole procedure out. You may go for a concession and say to your client, look, this is right on the money. We've got 1 point which is over the value. We want to accept it. Now, in many cases, if it came to me, I would actually be looking to reject the concession anyway. because 380 HV is really quite high, you know, this with the correct preheat values, the correct cooling rates, we should be able to meet that easily, hands down, in most materials. Even in stuff that's got a high carbon equivalent value, the right amount of preheat and cooling rates will get you to where you need to be. Sometimes it's frustrating to find that right level, but it is there, right? So the tests though will say you can retest and it might go away. You know, very often you have a failure, you say, right, we need to do a double retest, take it from some different places, and it's fine, and we rock on. Hardness testing on macros, of course, is a slice through a material that is not homogeneous. That means that the grain structure is different depending on where we take it. Just because we say it's made up of this composition, not every part of it is that composition, because the ingredients go to different places. Right, so with that long explanation, let's have a look at the answers. So accept it as it's only over the permitted value. That's not the answer, definitely not. Apply for a concession. Well, that falls into what I've just kind of said, but it doesn't mean it's the answer. Request a retest, reject the whole procedure. So, yeah, I would go for a retest first, and if my retest fails, then think about a concession if it's appropriate for the values I'm getting. So I'm going to say, ask for a retest. Cool. So normally in most standards, it's a double retest. So if you fail one, you'll do two. If you fail one of those two, your whole procedure's a reject and you start again. Right. You find several unacceptable welds and reject them. Oh, this is one we had the other day. So come on, let's take a second. What do you think you're going to do? Pause the video and you explain to me, even though I can't hear you, what you think should be done if a welding supervisor has overruled you and signed off the welds that you think are a fail. Okay, we'll give you 5 seconds. Right, so we're going to raise it with the issue with the QC department supervisor. Yeah, don't get into an argument. Don't fight it. Life's too short. It's not worth that. If he's wrong, he's wrong, and then we can deal with that elsewhere. Used to get angry about such things, and I don't think, what's the point? We just reject it elsewhere. In a fillet weld fracture test, the specimen is broken with. So a fillet weld fracture test, the specimen is broken with the fillet welding compression, the fillet welding tension. There's no specified method to adopt. This suitable machining, right? Not set of questions. So with a fillet fracture test, you're going to cut the weld down so it's got a notch in it, not all the way through, and then you need to apply force to that fillet weld to snap the plate off it using the notch as an intentional failure method. Okay, the standards, and I can't remember the number for the standard, but gives you kind of two main ways. One, which is a horrible way of doing it, is to hit it with a hammer to break the sample off. I think that's a bad way of doing it, even though it's what we were trained to do, because you've got inconsistent force. Swinging a hammer at something is just daft. We don't want to do that. The second method is to put it in a press after you put the notch in it and just force it down on itself so it's controlled, it's safe, you know where you are, right? So there is specified ways of doing that, so it's not that one, right? So is the fillet welding compression or is the fillet welding tension? Now, what you're doing is you're pushing the fillet weld back on itself to break it and pivot it. So I'm going to say it's in compression, which sounds weird for it snapping, but look, I think personally I would reword the answers to this, but we'll go with compression because that's the force we're putting on the weld. Okay, it's like the cap of the fillet is in compression, but the root is in tension as it gets pulled because the plate is moving across. I'd need to draw it out to kind of get it out of my head properly, but yeah. To assess the surface of a weld for direct inspection, the distance from the surface to the eye should be a maximum of. So this is in our standard. We read this and it'll tell us the angle and the distance away, and the answer for that is 600 millimeters. To me, that's still quite far, isn't it? Over half a meter away from a weld you're trying to inspect seems a long way. I would prefer to get a bit closer. You can't always, but if you can, it's better. Okay. Which of the following types of imperfection is generally considered to be the most serious? If you come to one of our classes, I'll give you a demonstration of why they're more serious. But a surface breaking surface breaking planar is the worst, right? Because it's a crack. It's a crack that's open to the world. So all of the force of any bending moment goes to the infinitely small point at the end of that crack. So all that stress on this very, very small point overcomes the fracture toughness of the material, and the crack can grow. Okay, so they're bad. A surface breaking non-planar is something like porosity. Because it's a rounded face, you don't have that single point to concentrate the stress. Root concavity, again, the same. That tends to be a wall thickness thinning issue. And a buried planar is a crack that's internal, or a lack of sidewall fusion that's internal. Instead of having one point to concentrate stress on, it's 2 points, so the stress at each point is halved. So if I was to go down sort of my risk list, I'd say surface breaking planar worst, then buried planar, then surface breaking non-planar, then root concavity. Would be kind of the way I see that. So surface breaking planar is the most serious. Which of the following is a quantitative test? I think we did this the other day again. It's tensile test. It's the only one we get a number from. Everything else on that list requires us to make a decision based on our experience and what we think it might be. So we'll get rid of that. Right. Narrow gap submerged arc. Which of the following is not true? Right. Here we go. Is a not true one. You watch part one, you see I've already screwed this up before, so I'm going to read it properly this time. In narrow gap submerged arc welding, which of the following is not true? It uses a special welding head. That is true. Operates only 2 wires. No, it can operate with 1. So let's see. It is used for thick plate. Yes, that is true. It requires a special flux. So the flux, because it's narrow gap, you want something that's not going to stick too much, and you want it to come out of that gap much more easily. Right. Now, so we're between these two. Operates only 2 wires and requires a special flux. So, which one are we going to go for? I don't like this because I've ran narrow gap with 1 wire, right? But in the main, it tends to be run with tandem wire, so twin wires, so two wires coming out of the same contact tip. Basically, it's like 2 flat plates, and your 2 wires come out as twin. Requires a special flux. Do you know what? I'm going to go with requires a special flux, but what should be this one? Yeah, there you go. Operates only 2 wires. Yeah, so the flux needs to be special because you need a flux which is going to remove or not bind in too much because it's a narrow gap. And of course, I've just answered my own question, haven't I? I said, look, I have used it as a single wire. I'm trying to overthink these too much. So there you go. Again, it's always good to see me get them wrong, isn't it? In submerged arc welding at high currents, or in the case of a multiple electrode system, AC is often preferred. Right, what this means is you have your first wire in your submerged arc head, normally pointing near enough straight down, maybe at a slight tilt each way, but vertically down. When we then put a tandem system in, that means we have another electrode with another wire coming into the same weld pool, and this weld pool gets really long. If you were to use DC positive as your leading and then DC positive as your trailing wire, those two arcs would interfere with each other, and what happens? If you try to push two same polarities together, they'll pull away and it'll create arc blow. So what we do is we use the leading wire is normally our DC positive, so we get the burning in and we get the penetration. And then the next one is more of a fill and run, so we don't need as much pen, but we need it not to affect the one. So AC is used a lot for that. So you get a little bit of penetration, a little bit of fill, no arc blow or reduced arc blow. Okay, so let's see what we've got in our list. Avoid the problem of excess pen. No. Avoid the problem of dilution. It's sub-arc. It's always going to have a high amount of dilution. Avoid the problem of arc blow. I like that answer. So let's go for that. Yeah. Right. We'll do a couple more and then we'll stop and do a part 3 because it's already on 40 minutes. Is it always necessary to preheat a base metal before welding? The answer is no, it's not always necessary. It depends on the thickness, the carbon equivalent, what we're trying to achieve, all these types of things. So preheating would be in accordance with WPS, would be my baseline. So let's have a look what the answer is. If using cellulosic rods, these would provide enough heat. Cellulosic rods burn hot, they get lots of penetration because they have a high amount of hydrogen in them. But it doesn't mean you don't have to preheat. Only in accordance with WPS, okay? If the equipment is available and must be used, not on a sunny day. I'm going to go with only in accordance with WPS because that's just our guiding statement, isn't it? If it's on the WPS, we do it. And we don't do anything else because it's been qualified, hopefully. Right, last one. The similarities... No, I'll tell you what, I'll go to 40 and then I know where I am. The similarities between ISO 22553 and AWS 2.4 in depicting weld symbols are. So what is the same between the two standards, right? Both have the same rule for depicting the other side. That's not true. AWS 2.4, it's always on the bottom of the line. In 22553 or 2553 now, it's on the dotted line, and that dotted line can be above or below. Right? Both have the same method. Is that not the same? Don't know what the difference between them two are. Both have the same rule for depicting all the way around, and both have the same rule for depicting sequence of operations. So I'll tell you that one's wrong because the AWS is a horrible system of depicting sequence of operations. It draws another line off the top and does all that. Okay, I need a whiteboard and some time to show you that. I would say, because I don't know what the difference between these first two top ones are, both have the same room for depicting other side, and both have the same method. Method of what? I'll go with both have the same rule for depicting a weld all the way around. Yeah, so it's a circle at the top of the arrow. Right. The depletion of chromium in austenitic stainless steel will leave a grain structure low in which of the following. So we've talked about that. So it's chromium. It's chromium oxide. So chromium, when it's subject to air, produces an oxide layer. That oxide layer is what protects the iron in our carbon steel and stops it from rusting and makes it stainless. So it's chromium oxide. I like seeing questions on weld decay because it does catch a lot of people out. It's a really quite a small subject. There's only a couple of things you need to remember: temperature, chromium chromium carbide is the thing that's produced, and the temperature for desensitizing is 1200 degrees. So if you heat it back up, it breaks those bonds again. For a bend test, which of the following is not true? The outer surface of the bend test specimen is examined. Yes, it is. The side that's in tension is the one we do. All right. It gives an indication of the ductility of the welded joint and welded material. Yes. It reveals defects of lack of fusion and porosity. Yes. A 4T bender is more severe than a 2T bender. Is that true or false? That's false, because we all laughed at me in the last video. There you go. I read it correctly that time. Okay, I like that. Prove I can actually remember something and answer a question correctly. Which of the following types of NDT does the term prod relate? So this is MPI. So normally we like to think of MPI with yokes. So a handheld, 2 legs on it, pull a button, spray, one person job. But one of the drawbacks with AC yokes is that the inspection area is not very big. It's just between the poles, the 2 legs that come down, 300mm type of size. What happens if we want to inspect something that's larger than that or more complicated, like a casting? Well, what we do is we have prods. So these are single poles which we can hold in each hand, put them onto the workpiece and energize. They work at huge amperages, like 1000 amps. So the coverage of the MPI is a lot bigger than what it is with a yoke. The problem is that you have quite a high chance of having arcing between the prod and the workpiece, and then we get arc strikes by trying to NDT it, which defeats the whole purpose of doing NDT. The main place we use this is in castings, especially just after they've been cast, and you want to check to make sure the casting's in one piece, it hasn't cracked or something like that. It doesn't matter in that case if we get a arc strike, because it's going to go through heat treatment and going to be machined and do all that type of thing. So that tends to be where they're used. But for us in oil and gas, pipelines, finished products, stuff like that, we want to use an AC yoke. Okay, so the answer here is MPI. Right. Which of the following defects are most difficult to size correctly when ultrasonic testing of welds? Ties into what we were saying before about volumetric defects, UT, RT, what they're good at picking up. Okay, so an isolated pore of 3mm diameter, lack of root pen, so we should see that quite easily. Cluster porosity, well, we should see because there's enough of it in slag. Well, I'm going to go with an isolated pore. They've got cluster porosity. That's because it's bigger than 3mm. I don't know. I would say if you've got cluster, that's a much bigger area. But to size it, yeah, I'll go with that. Again, don't mind admitting when I'll change my mind. So the idea here, I'm guessing by this, is that an isolated pore, you're going to get a feedback back into it, which you can pick up. Cluster porosity, as you drag your probe left and right, it's going to peak and down, and you're never quite sure if you're fully off the cluster porosity or on it. So to get the extremes of the far left and the far right, where is that? And how do we pick it up and we know we're not getting some random effect of making it look bigger or smaller? So we'll go with that one. I like that question because anything that catches me out, I do appreciate. Which test from below measures a material property known as fracture toughness. So fracture toughness, we talked about yesterday, is CTODs. I say yesterday in the video in part 1. Okay, we're getting there. Which is most accurate method of ensuring that the correct preheat is applied? Testing it, isn't it? Taking a measurement with a contact thermometer, because that's, you know, you get a reading, you know where it is, 75 mil away, and if possible on the other side, the back side of the plate or pipe. That's harder to do because we can't always get access like that. Okay, so if we go through the answers, measurement with temp sticks. Temp sticks are good, they're portable, you don't have power. Drawback with them is you only know if you're higher or lower than a temperature, but they're quick measurements. Am I above 50 degrees? Yes. Am I below 100 degrees? Yes. What is my temperature? I don't know. Using heat treatment equipment with thermocouples attached to a chart recorder, by far the most accurate and best way of doing it. More expensive, not, I'm going to say not portable, because you've got to take it, you've got to put your studs on, connect your thermocouples, do all that, have some equipment. But if you want accurate, that is the best way. The best way for us on site is a digital thermometer, contact thermometer, right? And that'll get us there. Temperature measuring paint, yeah, it doesn't tell you what temperature it is, so I wouldn't go with that. So for the most accurate, by far, it's heat treatment thermocouples. Yeah. The worst one to use is laser guns. Just don't do it, please. If I see you on one of my sites doing it, I'm going to slap you. Right? The heat guns take a large area. They're limited on distance. They're affected by the surface finish and how much they reflect or don't reflect. They're just rubbish. They're for doing DIY stuff or checking the temperature of buildings rather than doing what we're doing for preheats and interpasses. A weld all-around symbol is not required. And again, we did this one in part 1. Is not required when indicating a nozzle to a shell, indicating a pipe butt, so all of the above. Yeah, cool. Right, last one for today then. Which of the following will help reduce distortion? Using a high heat input. Sounds like that might not be the best idea. Welding with a manual method. Doesn't really matter. Using the minimum number of runs. Yeah, I think did we do this question, or do we do something similar to it in the last session? The minimum amount of runs means that we've got minimum contraction phases, so that will give us the least amount of distortion. But we won't get a good amount of weld. Word I'm looking for has gone out of my head. Recrystallization and making it better. So that's going to be a drawback for that. Right. Okay, so we will finish there. This is going to be our next question. So which of the following could be used to minimize the occurrence of solidification cracking when we do part 3? Hopefully that is another set of questions. Again, you can see, continue to say I don't always get them right, but it's about learning the questions we get wrong. If you have any questions, drop it below. Thank you for the really cool reception the last got. It was the most viewed video within the first 3 hours of uploading that we've ever had, which is great. Keep them coming, keep them watching, and I will see you in the next one. And good luck with your studies.